The next question is, a mass m hangs with the help of a string wrapped around a pulley on a frictionless bearing. The pulley has mass small m and radius capital R. So, there is a pulley, the pulley is a disc and it is fixed. The pulley has mass small m and radius r, so mass of pulley is m and radius r. Assuming pulley to be perfect uniform circular disc, the acceleration of the mass small m. So, a mass small m is hung with the help of a string which is wrapped over the pulley, this mass m. So, as this mass goes down, the string will unfold. Now, as the string unfolds, the pulley or the disc will rotate about its center, and for rotation the torque is provided by the tension in the string. So, torque due to tension will be Tr, and you know torque can be written as I alpha. So, this is equal to I alpha, or tension, from here tension is equal to I alpha upon r, and moment of inertia for the disc about its center is half mr square, or leave it here, we will use that later on. Now, as this mass goes down, you can write mg downwards, tension upwards. So, you can write mg minus t is equal to ma. You need to find this acceleration a. Now, put the value of t here, which is mg minus I, and the acceleration of the string is a, which is tangential acceleration. So, tangential acceleration and angular acceleration are related with this expression, a is equal to r alpha, where alpha is angular acceleration. So, from here you can see alpha is equal to a upon r. Okay, then t is equal to I alpha upon r is equal to ma, or mg is minus I, which is half mr square, and alpha, which is a by r, and this r will be r square is equal to ma. Now, mn, they get cancelled out, and r square also get cancelled out. G is equal to, here it is a by 2, which you take from this side. So, a by 2 plus a is 3 by 2a, or a is equal to 2g by 3. So, the downward acceleration of the small mass of the mass small m is 2g by 3. Next question. Next question. A pulley of radius 2 meter is rotated about its axis by a force. So, force acting on a pulley is 20 T minus 5 T square Newton, where T is measured in seconds applied tangentially. So, this force is applied tangentially, then the torque due to this force will be F into R. If the moment of inertia of the pulley about its axis of rotation is 10 kilogram meter square, the number of rotations made by the pulley before its direction of motion is reversed. So, from here you can see torque is equal to F into R, and is at the place of torque we can write I alpha, which is equal to F is 20 T minus 5 T square into R. Now, put the values. So, alpha comes out to be I is 10, R is 2. So, you are left here with 5. So, this whole thing will be divided by 5, then it becomes 4 T minus T square. So, alpha is equal to 4 T minus T square, and alpha can be written as d omega over dt, or d omega becomes 4 T minus T square whole into dt. When you integrate this expression for some time t, you get the value of omega at some time t. So, integrating this expression, this is just 4 t. So, this becomes t square by 2, which is 2 t square, and this becomes t cube by 3. So, this is angular velocity at any time t. Now, you can see angular velocity will be 0. From 2 t square some t cube by 3 is subtracted. So, you can see that omega will eventually become 0 at some time. Let us calculate. So, put this is equal to 0. So, put omega is equal to 0, then you find t is equal to 6 seconds. So, when omega becomes 0 and after that, after 6 seconds, this term will be more than this. That means the motion gets reversed. The angular velocity is changing its direction. That means you need to find the number of rotations from 0 to 6 seconds. After 6 seconds, the motion is reversing. Okay. And more omega can be written as d theta over dt, which is 2t square minus t cube by 3, or d theta can be written as 2t square minus t cube by 3 whole into dt. When you integrate this, you find the angular displacement. So, you have to integrate this from 0 to 6. Now, this is t square, it becomes t cube by 3. So, 2 by 3 t cube from 0 to 6 minus this is t cube by 3. So, this is t raised to the power 4 by 4 and 4 into 3 is 12. So, 1 by 12 into t raised to the power 4 from 0 to 6. Now, from 0 to 6, that means t is 6 cube, and 6 cube is 216 minus 6 to the power 4. So, 1 upon 12 and 6 to the power 4 is I think 1296. 1296 is 6 to the power 4. Now, this is 144, 72 into 2 is 144, and this is 108. This is 108. So, the angular displacement for 6 seconds is 36. Then number of rotations, there is 2 pi displacement for one rotation. So, number of displacement will be 36 divided by 2 pi, and 2 pi is 6.28. The denominator is more than 6. So, the whole ratio will come out to be less than 6. If it is 6, the ratio is 6. Now, if the denominator is more than 6, the ratio is less than 6. So, number of rotations made by the pulley is less than 6. Next question, a hoop of radius r, a hoop is a ring, and mass is small m, rotating with an angular velocity omega naught, is placed on a rough horizontal surface. The initial velocity of the center of the hoop is 0. What will be velocity of the center of the hoop when it ceases to slip? So, a hoop initially rotating with an angular velocity omega is put on a rough surface. So, initially it will slip and eventually it will start rolling. And when it is slipping, this part is going backward. So, the frictional force will be in forward direction, and frictional force, it is a case of slipping, frictional force will be mu mg. Now, if frictional force is mu mg, then only the friction is in forward direction. So, it is the net force, then the acceleration due to frictional force will be mu g. And you can see the rotation is clockwise and the torque produced by the frictional force is anti-clockwise. So, the torque due to frictional force is causing the motion to decelerate. Okay. So, causing an angular deceleration. Now, torque due to the friction is Fr. F is equal to mu mg into r, and torque is equal to I alpha. So, alpha is equal to mu mg into r upon I. Moment of inertia about this axis is, this is a ring, moment of inertia about this axis is mr square. So, just mu g upon r. The angular deceleration is mu g upon r. You have angular acceleration, you have angular deceleration, which is mu g upon r. Let us calculate angular velocity as well as linear velocity after time t. So, the linear velocity after time t will be v is equal to u plus at. Initially the center of mass has 0 velocity. So, velocity after time t is acceleration times t, acceleration is mu g. So, mu g into t, and the angular velocity after time t, omega is equal to omega naught minus alpha t, because it is a case of angular deceleration. So, omega naught, omega is equal to omega naught minus alpha t, alpha is equal to mu g upon r into t. Now, for the case of pure rolling, let us say after this time the body starts rolling, purely rolling, then for rolling you have the relation v is equal to r omega. Now, v after time t is mu g t, this is equal to r, and omega after time t is this omega naught minus mu g upon r into t. Now, this becomes omega naught r minus r get cancelled, mu g t, and this mu g t comes over here, it becomes 2 mu g t, or t is equal to omega naught r upon 2 mu g. This is the time after which the body will start rolling, it will start moving as pure rolling. Then at this time you need to find the velocity of the center of mass. It is very easy, mu g into time, which is omega naught r upon 2 mu g. So, the answer is omega naught r upon 2. The angular velocity, the velocity of the center of mass when the body starts rolling is omega naught r by 2. Next question. A bob of mass small m attached to an inextensible string of length L is suspended from a vertical support. The bob rotates in a horizontal circle with an angular speed omega radian per second about the point of suspension. So, it is a case of conical pendulum. A bob is suspended like this and it rotates in a horizontal circle. So, it goes like this. Okay. When it is rotated, the bob or the particle goes in a horizontal circuit, it is suspended from a vertical point. Okay. Like this, there is a particle and these two forces are acting on the particle, tension in the string and gravitational force, the weight. Now, there are some options. So, let us see what is the direction of torque and what is the direction of angular momentum. You can see torque about this point is r cross mg. So, torque is outward, that means this mass will tend to move clockwise, it will tend to move anti-clockwise. This mass will tend to move anti-clockwise due to this weight, and tension is passing through the point about which we are calculating torque. So, torque due to the tension in the string will be 0, and torque due to the weight is tending to move the block, to move the mass clockwise. Now, what about the angular velocity? Angular momentum. Say this particle is going in, it is going in, the velocity vector is inward, then angular momentum is r cross p. Now, if the particle is going in, linear momentum is inward, p is inward, and this is the position vector. Now, r cross p. So, the angular momentum comes out to be in this direction, and torque is outward, and angular momentum is r and cross p. So, this comes out to be somewhat along this direction. Now, this direction is in the plane and this direction is out of the plane. So, certainly the angle between the torque and angular momentum is 90 degree. Torque and angular momentum are perpendicular in this case. When they are perpendicular, when force is perpendicular to the velocity, it cannot change the magnitude of velocity, it only changes the direction of velocity. Similarly, when torque is perpendicular to the angular momentum, it cannot change the magnitude of the angular momentum, it can only change the direction of the angular momentum. So, the correct answer will be angular momentum changes in direction. The torque is perpendicular to the angular momentum, so it will change the direction, but not in magnitude, okay, because they are perpendicular. Next question. Distance of the center of mass of a solid uniform cone from its vertex is z naught if the radius of its base is r and its height is h, then z naught is equal to. So, center of mass for a solid cone from the base is h by 4, and from the vertex it will be 3h by 4. Next question. Now, this question is, let me first make a diagram. So, this is the question. Okay, now the question. A roller is made by joining together two cones at their vertices O. The vertices are joined. It is kept on two rolls AB and CD, but you can see the rails are not parallel. It is kept on two rails AB and CD, which are placed asymmetrically with its axis perpendicular to CD and its center O at the center of the line joining AB and CD. It is given a slight push so that it starts rolling with its center O moving parallel to CD. So, this center is moving parallel to CD. As it moves, the roller will tend to. Now, at this double cone or the roller goes on, it will be at some point, at some point of time it will be here, okay. The roller will be here. Now, previously the wider part was on the rail, now a narrower part of the cone is on the rail. So, when the narrower part is on the rail, the radius of the rolling part is decreasing, and for rolling V is equal to R omega. When radius is decreasing, certainly V will decrease because omega is locked. Both the cones are joined at their vertices. So, whatever be the angular velocity of this part will be the angular velocity of this part. So, if radius of the part that is on the rail is decreasing, then certainly the velocity of the part will also decrease. So, velocity of this part, you can see the narrower part is on the rail. So, radius of the cross section that is on the rail is decreasing. So, velocity will decrease because omega is locked. Now, as the velocity is decreasing of the left part, the velocity of this part will keep the same value, and it will move forward. It will be left behind, and when it is left behind, it moves forward. The whole thing seems to tend towards the left side. So, the answer is this double cone roller will tend to turn left. Next question. Energy required to move a body of mass small m from an orbit of radius 2r to 3r. So, this is a very simple question. The energy required will be change in potential energy. Initially, it is in the orbit of radius 2r and finally in the orbit of 3r. So, potential energy is minus g small capital M small m upon, finally it is at 3r. So, final potential energy is minus gmm upon 3r minus gmm upon 2r. So, minus gmm upon r, we take it common, and here it is minus 1 by 3 and here it is plus 1 by 2. So, plus 1 by 2 minus 1 by 3 is I think 1 by 6. So, minus 1 by 6. So, the answer is G capital M small m upon 6r. This much energy will be required to take the mass from an orbit of radius 2r to an orbit of radius 3r. Next question. Two spherical bodies of mass capital M and 5m and radii r and 2r respectively are released in free space with initial separation between their centers equal to 12r. If they attract each other due to gravitational force only, then the distance covered by the smaller body just before collision. We have done this question in the previous segment. The question is unfortunately repeated, so you can check the previous video to find the solution of this question. Next question is, a satellite of mass small m revolves around the earth of radius r at a height small x from its surface. If small g is the acceleration due to gravity on the surface of earth, the orbital speed of the satellite. Now, if a satellite is at height x from the surface, then gravitational force on the satellite will be gmm upon r plus x whole squared. Now, this force will provide the necessary centripetal force for the satellite to move in orbit. Now, the centripetal force for the on the satellite will be mv square upon radius of the orbit, which is now r plus x. So, you can see v comes out to be, here it is just r plus x. So, v comes out to be g capital M upon r plus x. Now, multiply the whole thing by, multiply and divide by r square. So, gm upon r square becomes gravitational acceleration at the surface of earth. So, it is g times capital R square upon r plus x whole to the power 1 by 2. The whole thing is under a square root. So, the answer is fourth one. Next question. Suppose the gravitational force varies inversely as the nth power of distance, then the time period of a planet in circular orbit of radius capital R around the sun will be proportional to. So, we know the force, gravitational force varies as 1 upon r square. Now, in this question it says it varies as 1 upon r to the power n. The gravitational force varies inversely as the nth power of the distance. So, gravitational force varies as 1 over r to the power n, or you can write F is equal to k upon r to the power n. K is some proportionality constant. Then you need to find the time period, how time period depends on the radius or on this value n. Now, this force will provide the necessary centripetal force mv square upon r. So, v square here is equal to this is r upon r to the power n. So, r to the power 1 minus n, and k over m will become some another constant. So, we can write it at alpha. Alpha times r to the power 1 minus n, this is v square. So, v is equal to alpha times r to the power 1 minus n and whole thing divided by 2. Okay? This is a constant, square root of constant is also a constant. So, this is velocity alpha times r to the power 1 minus n upon 2. Let us write it alpha dash. Now, the time period will be distance upon speed. Distance for a distance in an orbit of radius r will be 2 pi r, and if speed is v, then 2 pi r upon v is time period. Then 2 pi r upon speed, which is alpha dash times r to the power 1 minus n whole thing divided by 2. Now, 2 pi upon alpha dash is some another constant beta, and this thing goes up. So, it becomes r to the power 1 minus half is half and plus n by 2. So, this is n plus 1 by 2. Okay. So, from calculation it will come out to be r to the power n plus 1 by 2. So, time period is directly proportional to r to the power n plus 1 by 2. If force is varying inversely as inversely as 1 upon r to the power n, then the time period will be proportional to r to the power n plus 1 divided by 2. Okay. Then the next question, what is the minimum energy required to launch a satellite of mass small m from the surface of a planet of mass capital M and radius capital R in a circular orbit of an altitude 2r. So, there is some planet mass m, radius r, and a satellite is to be launched from the surface to an altitude 2r. Then the radius of the orbit will be 3r. Then what is the energy? Now, from conservation of energy, total energy at the surface of the planet should be equal to total energy in the orbit. So, total energy at the surface should be equal to total energy in the orbit. Now, total energy at the surface is minus g capital M small m upon r, and energy provided to the satellite in the form of kinetic energy half m v square. This is equal to okay. So, this is equal to potential energy g m m upon radius of the orbit, which is 3r plus half m v orbital square. Okay. So, we can calculate the velocity because the centripetal force will be provided by the gravitational force. So, gravitational force in the orbit will be g m m upon distance is now 3r. So, 9r square. This will be equal to m v orbital square upon 3r. So, 3 times 9 and r, small m gets cancelled. So, orbital speed or v naught square whole is g capital M upon 3r. We can use this v square here. So, this is minus g capital M small m upon 3r plus half times small m and then g capital M upon 3r. Now, you can see minus g capital M small m upon r plus half m v square, m gets cancelled out everywhere, and from here you can calculate v square in terms of g, m and r. So, from calculation, now this is just a part of calculation, from calculation this thing comes out to be 2, in fact they are asking energy, not speed, okay? Energy. So, you have to calculate this whole thing half m v square. So, let us just write it k. So, you need to find k. Okay? In that scenario, m will not get cancelled. Okay? So, you need to find the whole kinetic energy, not just speed. Of course, you can do calculations in terms of g m small m upon r. Then after calculation, it comes out to be 2 capital G capital M small m upon 3r. This is the answer. Next question. Four particles, each of mass capital M and equidistant from each other, move along a circle of radius capital R under the action of their mutual gravitational attraction, the speed of each particle. So, particles are on the circle symmetrically such that they form a square. They form a square. Okay? For each of mass small capital M equidistant from each other. So, this fulfills only they happen to be on the corners of a square. Okay. And the radius of the circle on which they are moving is r. Under the action of their mutual gravitational attraction, the speed of each particle is. Okay. So, the speed of each particle. Now, you can see this is radius r. and this whole thing is R